Hello, everybody, and welcome to this session of Autodesk University about efficient and consistent MEP engineering calculations directly inside Revit. My name is Toon Demuynck, and I'll be presenting you this session. So first, a few words about who we are and what we do. What we try to do specifically regarding this session is we try to reduce the effort to do the usual and necessary and increase the time to be creative. We didn't invent that phrase, it was Tristan who invented it. Where do we work? We work at Arcadis, which is a rather large sustainable design, engineering and consultancy company for natural and built assets. We have around 27,000 people in over 70 countries. My colleague will also be joining in the live session. His name is Vasile. He works in Romania, also for Arcadis. There he is an MEP engineer, also a very high-level BIM and Revit expert, and he has a constant strive to improve efficiency. Myself, I work in Belgium. I started as an MEP engineer, and currently I'm a BIM coordinator and also a design automation lead for Belgium, and I share the same strive to improve efficiency. So let's get started with the actual session then. I want to start out with the different learning objectives that you've probably seen and why you are joining this session. So first, I would like to talk about the benefits of integrated engineering calculations so that you can better understand what those benefits are or might be for you. Secondly, I would like to show you some general possibilities of those integrated engineering calculations, where I'll briefly talk about what we currently do at Arcadis. Then I want to speak a bit about how you could integrate your own engineering calculations in Revit, what you have to think about, what you have to be careful with, etc. And then lastly, the major part will be the practical integration of those calculations in Revit. So there you will see how we currently integrate, which calculations we integrate, and how we do that practically, really detailed. So first one are the different benefits that we see that come from integrating those calculations inside Revit. First one is repeatability, of course, compared to a classical way of working where people have their own methods of doing some calculations. If you have engineer A, engineer B working on the same project in a different point in time, might be that it's not very repeatable and that the results might differ a bit. So the second one is also linked to that, which is consistency. If somebody else or yourself has to do the calculation again, it will be consistent because there's a documented workflow. It might be hard-coded in scripts or in schedules, etc. This will also improve the quality because if you have a documented workflow, you will deliver a higher quality of work, and also, and very importantly, will increase our efficiency, because the goal is, of course, to work more efficient so that we can spend more time on being creative. Since we will be able to work more efficiently, we will be able to respond easier to design changes, which happens quite a lot in a lot of projects. We will also reduce repetitive work because sizing ducts, for instance, is quite repetitive. I have to add up all airflows, etc., calculate air speeds, size your duct, which is quite repetitive. If we can automate that, integrate it in Revit, which will make our work a lot more fun to do. All those things will also lead to improved customer satisfaction because we will be able to respond to design changes instead of having to say, no, we cannot cover this change anymore. It's too late. We have to deliver in a few weeks. And ultimately, all of those things will also result in a better operational margin of our division or the complete company. And last one, I also added generative design with a question mark because we feel that integrating those calculations in Revit or in any software, but integrating them together in one model is a needed first step to later on move to generative design. Okay, next, a bit about the general possibilities, what we currently do in Arcadis and what we are planning to do or what we're already working on, but it's not finished yet. So we have here our complete portfolio, so to speak, of engineering calculations, which I will go through in different slides on how we tackle them. So the next one, pipe sizing for heating and cooling pipes and duct sizing for ventilation systems. We do that with standard Revit functionality. It's basically a standard function that's available in Revit that you can use Just have to make sure that you connect everything correctly, etc. So next one, lighting calculations, mainly indoor lighting in offices, etc. For that, we currently use a commercial add-in, which is Illum Tools, an add-in in Revit, where we can also use our same Revit model to do the lighting calculations, which is the same model that we will use to do our heat load calculations, which is the same model that we use to do our coordination with the different disciplines, etc. And then last, we have our in-house developments, where the red ones indicate the developments that we already use or actively using, which is the pipe sizing, but then for water supply pipes and drainage pipes. The cable length calculation tool is a Dynamo script that we've developed to actually route cables over cable trays, calculate the lengths, visualize it, etc. Also, we calculate the ventilation rates according to the Belgian code. The first development is. And then the three ones in orange are the ones that we're still working on. And the one in the middle for regarding the heating and cooling loads calculation is already quite advanced. It's ready to be released in the coming weeks, actually, and I will also show what it currently looks like and what the status is. And then two other ones that are in the pipeline to be developed are equipment selection and component placement. I will talk a bit more about that later on. So this is just to give you a general idea of what I'm talking about when I say engineering calculations. It's these type of calculations or actions, because component placement is not really a calculation, but it's also something typically done by an engineer, at least in Belgium. So if you want to start developing your own calculations inside Revit, you really have to think about the calculations that you perform and how you perform them, or your team, of course, because if you're a BIM coordinator, probably you're not performing too many calculations yourself, but your MEP team is probably doing a lot of calculations. You will have to work together with them. So you have to really know what you're doing and how you're doing it. First, you have to think about the relevant design stage that you're working in. If you're a company that's generally working in conceptual design stages, or if you're typically working, if you're a contractor, you're typically involved in the actual execution of projects, and you need really detailed execution designs, because this will determine with type of elements you'll be working in Revit. In the conceptual design phase, you'll have general high-level components like spaces, space reservations, etc. And in the latest phase, in the execution design, you will have really detailed families with the detailed geometry. You might need more geometry information than you need in the normal detailed design. So that's all something that you really need to think about. Also, you can check if you calculate everything according to international or national standards, because if that's the case, then you have a higher chance of commercially add-ins being available. Then you can see if it makes sense to buy them or not. If they're too expensive, then maybe you can create something yourself with your team. If you do calculations based on experience, then the only possibility you have is to develop something yourself or outsource it to another company. Then you have to clearly state what you expect to be programmed, which is a rather large pitfall that you have to mind. Another possibility is that you work with calculations that are done by manufacturers. In that case, sometimes it's problematic to get the details. So then you will have to talk to the manufacturer that you are in contact with, if they are able to share the details of the calculations with you, so that you can integrate it into Revit. You can work together with manufacturers or suppliers to do that. But you really need all the details of all the calculations before you can think about integrating it in Revit. Otherwise, it doesn't really make sense to integrate anything in Revit. Another pitfall can be the complexity of the calculations. If you have like really complex calculations, I'm thinking, for instance, sound calculations, it can be the case that it's simply too complex to be integrated into Revit. So certainly, if you have complex calculations, don't start with those. Start out with the easier ones, that you get some experience on how you can integrate it, and then maybe make the step to the more complex calculations to be integrated in Revit. Okay, now I'll talk about the practical integration of those engineering calculations in Revit. So first, I'll have some technical aspects on the integration. So I'll basically go over those different options that we currently have to perform calculations in Revit, and I try to put them in order of increasing complexity. The first one being the standard Revit functions that we currently use for pipe and duct sizing, the heating and cooling pipes and the ventilation ducts, so the air handling ducts, etc. Next in the list is existing or commercially available add-ins. Some add-ins are free, some are paying. Can go from very cheap to really expensive. Most of them you can find in the Autodesk App Store, but some of them are also only available through the websites of the suppliers. The next one, and then I get to the ones that we develop ourselves, are schedules with calculated parameters. So we basically set up a schedule where we calculate some values based on other values in the schedule for pipes, for instance. Next one is to develop some Dynamo scripts to do some of the work for us. And the most complex one is where we actually develop add-ins to do some calculations for us in Revit or to assist us in doing calculations. So first, standard Revit, pipe and duct sizing. Here on the right, you can see the icons that we use. This is the duct and pipe sizing icon in Revit. Like I said before, it's a standard Revit function for heating and cooling pipes and ventilation ducts. You can do the sizing based on pressure drop and or velocity in the pipes or the ducts, whichever your local code requires you to do. You do, however, have to be very careful that the families that you connect into your pipes and ducts, that they have the correct flows, fluid or air, and that those systems are connected completely and correctly. Because if your system is not completely correctly connected, then you might get very strange results because Revit doesn't know if the flow has to go to the left or to the right, for instance, if you have two open points in your piping system. You can check that with the system inspector tool, where you can check the critical path, etc. And it's also a very good first check to see if your system has been connected correctly, because if you select a system and the system inspector icon does not show up, that means that your system is not correctly connected. So then you need to close and open and typically or connect something that where the pipe or the duct is very close to your family but not logically connected. So then you need to check those. You can also switch on the option in Revit to show the open ends, which is also very helpful. And also your system browser with the F9 shortcut also makes a lot of sense to check how your systems are connected and how they're doing in Revit. What we typically do in most cases is we set up some color plans for the engineer to reflect the pressure drop or velocity for easy checking, so that he can easily check with one view on a plan, is the velocity low enough, below spec, or there's some problematic areas where we have too high speeds or velocities. Same for the pressure drops, if they're in spec or not. What we also do in some cases is, for instance, for piping or for ventilation, we create a parameter for all ducts, and we give it a name or a value: branch, main, or shaft, because typically in a ventilation branch you have different allowed air speeds than in a main duct or a duct in a shaft. And that makes it easier to select those ducts. If you say for one project I want to select all my ducts in a shaft, then you can simply create a filter or a view where you only have those ducts with the parameter main. And then you select them and then you run the pipe or the duct sizing tool. What's also very handy is a selection tip in Revit. If you want to select a piece of pipe or duct between 2 points, you can select the first one, then hover over the last one, then click tab, and then click with your mouse, and then you select everything in between. You will show it you will see it in the screenshots later on with an example what I mean by that. Also, we've noticed the need to use diversity factors. For instance, if you have a ventilation on an office floor where you have 10,000 cubic meters per hour, and you have 10 of those floors, then your air handling unit will probably not be 10 times 10,000. It will maybe be 70 or 80,000. So on every floor, you can set a family or connect a family into the ducting system that applies that diversity factor. The backside of that is, of course, that it actually does create two different systems. So you don't have one ventilation system, but everywhere where you put one of those families that splits it up, you have one system on the left side and one system on the right side. So if you want air volumes in your system or fluid volumes, you have to add up some different systems for which you can create a script or an add-in, of course. This is what it looks like in Revit then. Here you see, I will quickly show my pointer. So what's indicated in red here is a piece of duct sections that I selected with the trick that I said earlier. So I just click on this one, then I hover over this one and press tab, and then I click again, and then all those ducts in between get selected. Those are the main ducts in a lowered ceiling. Here I have a speed, for instance, of 5 meters per second. I can also take the pressure drop in the ventilation ducts into account. I can restrict the height and the width, or I can also say if I would be sizing a branch to match the connector size, or to actually calculate it, or to take the maximum of both of the calculated size of, or the connector size of that air terminal. So those are the settings that you can make here for duct sizing. Then you can just press OK, and the duct gets sized. And then you can have a color plan with the speeds or pressure drops, whatever you need. You can check for clashes to see if any clashes have been created with the sizing, etc. Then this example is looks a bit the same, but it's for heating and cooling piping. So here I selected this run of pipes, again with the same trick with the tap and then the both ends of the pipe. Here I can size on friction and or velocity again. Here we're now sizing on a pressure drop of 120 Pascal per meters. You can also restrict the size. Of course, you don't have a height and a width because pipes are typically round and not rectangular. So, but for the rest, it's more or less the same than when you're sizing ducts. There are, however, some points of attention when you use this functionality of pipe and duct sizing in Revit. You have to use your mechanical settings and your systems correctly. You have to set all the parameters, the air density, fluid density, roughness of your pipes, etc. All of them have to be set correctly. And also in your systems, you have to select the correct fluid, water or glycol or whatever type of fluid you set up here in your mechanical settings. Here you set up your fluids, and here you select the fluid that you want to use in your system, and also you set the temperature of that fluid, and based on that it interpolates and calculates the dynamic viscosity, the fluid density, etc. If you want to calculate pressure drops, you also have to select the correct loss calculation method for your fittings. So all your T's, bends, elbows, etc. You need to select the correct loss method to be used. And for pipe sizing in heating and cooling systems, it can be that the supply and the return pipes have different diameters when you size them, because they typically have different temperatures, and because of that different temperature, they also have different viscosities, different pressure drops. So it can be that one is one size bigger than the other. Then that's most likely because of that difference in temperature, and hence also difference in viscosity and pressure drop, which of course only will happen if you're sizing on pressure drop. If you're just sizing on speed or velocity, you will not see that behavior. But we noticed that in some projects that we have different sizes for that. You can then choose to keep the different sizes or to actually make them the same size. Then something about commercially available add-ins. I also included some useful add-ins which are not really integrated calculation tools that we use, but I just wanted to give them because they're very useful to us. But actually they're model authoring tools like PyRevit and all the ones linked, or sub add-ins from PyRevit MEP, PyRevit Plus, PyRevit Structure. We also use Microdesk, TI Roots, and Bird tools, and there we mainly use the clash preventer, which actually helps us prevent clashes instead of solving clashes later on. Of course, there's also other tools that probably do the same, but this is just a selection of what we currently use. One of the calculation tools that we use, add-ins, commercially available add-in in Revit, is Illum tools, and we use that to perform lighting calculations, mainly internally inside buildings. You can also do external lighting calculations, emergency lighting calculations, etc. And the big advantage there is that it's using the same architectural model in Revit, the same building model in Revit that we use for our other calculations. For instance, the ventilation calculations that we do to determine the ventilation rates is based on the same model. We have really one source of truth. Everything is based on that one same Revit model. And that's one big advantage of those integrated calculations. I will not show more information about those add-ins because there's a lot of information available on the internet. If you're interested, you can certainly look that up, but I think it will be more interesting to have a look at how we integrate our own calculations, because it's of course easy to buy an add-in and learn how to use it, but I think most people want to know how they can integrate their own calculations in Revit and not how they have to buy an add-in. So the first one that I want to show you is how we work with schedules to do engineering calculations. It's, in our opinion, very easy to use and set up. If you can create a schedule in Revit with a calculated parameter, then you can set up a schedule like this. Of course, you need to know the formulas to use, and you need to have some common sense to apply them correctly. We use them for two situations currently: sizing of pipes for water supply and water drainage, and also for the calculation of ventilation rates according to the Belgian codes, which is EPP. For the pipe sizing, we use a parameter in Revit, which is called fixture units, as that parameter in a piping system is just added up by Revit. So if we click any pipe in Revit, we can always see the sum of all the flows that is going through that pipe. So if you have like 10 fixture units connected to all those sub pipes, then you can see 10 fixture units in that pipe. And then from that sum of all the flows, we can apply any formula according to any standards that we need to convert that total flow into a peak flow. I will show some more details about that later with some screenshots. And then the ventilation rates calculation is based on space types that we select in a schedule. And then we have some logic in the schedule, which is very Excel-like. It looks like a spreadsheet. And based on the space type that you select, the requirements are then calculated based on the area of that space and the type that you selected, because it's quite clear that a meeting room will need more ventilation per square meter than, for instance, a normal office space, because a lot more people can be in a meeting room than in a normal office space. I will give some more information now first about water supply pipes. For that to work, we need, of course, families. Here on the left side, there's a family of a wash basin with cold and hot water phase-based and also a waste drain connected. And we have here three type parameters for that. WFU stands for waste fixture units. This is the hot water fixture units and the cold water fixture units. So in Belgium, Europe, these are the values that we have to work with: 0.07 liters per second for cold and hot water for just a wash basin. Here we have a mechanical equipment, and here the value for this small water boiler is hard-coded in the family. There we say, okay, this connector has a fixture unit count of 0.07. You can link it to a type parameter, which is what we did here on the left side. But that was just to show you that you have two different options to actually enter the values that you need the family to put into the piping system for the rest to work. Then here I want to show you how we actually configure our schedule. The schedule itself will be visible in the next slide, but I first wanted to show you how we configure the schedule before I showed it to you. So here you have the list of all the parameters that we show in the schedule. The first one is the total flow. We set it equal to the fixture units, but you see it's a number, it's not a flow, because if you would say it's a flow, then you cannot say it's equal to fixture units, because fixture units and flow don't have the same dimensions in Revit. So we just define it as a number. Here's where we actually apply the formula that we want. This is a formula that's used in office buildings in Europe. So it's just with some parameters and a formula that you can find. Also, it's a number again. That's why we also add the liters per second between brackets to know that it's liters per second and not cubic meters per hour or something. So here we have the peak flow, which is not the sum of the flows, but a simultaneity factor applied to it. Here we then have the peak speed, which is based on the peak flow and the inside area of the pipe through which the flow is going. So here we calculate the peak speed. And then something also very important here is that we sort and group by section, because pipes are also assigned a section in Revit. And a section of pipe is actually, if you have like a section of pipe running with a few bends in between, it can be 10 or 15 different pipes that are connected with elbows. But all those pipes have the same properties. They have the same diameter, the same flow, the same fixture unit count, etc. So we group them by section and we do not itemize every instance. So then all pipes are grouped per section. So then your schedule to go through becomes a lot smaller. Then you don't have to select every pipe individually, but you can just select every section. That will be clear in the next slide. Here on the left side, you see the 3D view so that you can actually see what pipe you're working with. So here on the right side, you have one line, so one section. Here you see the section number 245. It's this section of pipe. So it's actually 1, 2, 3 pieces of pipe in this section. Here we can see the peak flow and the peak speed. And in this system, the peak speed needs to be below 1.5. So here the user knows, okay, if I will decrease this from 25 to the next smaller size 20, it will probably be higher than 1.5. And then it will be red. And then you know, okay, no, it needs to be 25 millimeters. And you just basically have to go through the list, not from the top, because of course you have some pipes in Belgium, the connection pipes, for instance, to a shower, they always have the same fixed diameter of 16 millimeters. So you don't have to go through all the pipes which have a diameter of 16 millimeters or a fixture unit that you know is just one wash basin or one shower, etc. So we can start somewhere halfway the list, go through it, change the diameter until your speed is low enough. And that's basically it. You don't have to draw any schematics anymore. You don't need an engineer to add up flows, etc. So not needed anymore. So that was an example of how we use calculate values in schedules. Now I want to show you some more about scripts and add-ins that we've developed. A script that we also use a lot is a script to transfer data from spaces to equipment. For instance, ventilation rates, they can be a space parameter, but actually we need that value to be in the air terminal because the air terminal needs to deliver the air into the space or extract it from the space. So there we have a script that checks which air terminal is in which space, and then it copies the value from the space to the air terminal, and then that information can be used to size the ducts. We also can develop some scripts to calculate the required diameter of a pipe. Instead of manually selecting it, we can calculate it and add it as another column in that schedule, and then you just have to select the same diameter as the one that's calculated. Why do we want to do it like this? This is mainly for drains sizing, because if you're automatically changing diameters for drains, then you can get quite a lot of connection errors in Revit. So that's why we want to make the step in between to have a manual check in between. What we're currently working on is an add-in for a heat loss calculation based on the European standard. For that, we use the Revit analytical energy model, which is generated from a building model inside Revit. If you want more information on that analytical energy model and Revit systems analysis, you can go and find this presentation in Autodesk 2019, System Analysis and Introduction by Ian Malloy from Autodesk. And this is the European standard that we use, and it's currently in final stage of development before we need to still test it and before it can be released. We have a similar add-in where we calculate the cooling loads, which is based on the same analytical energy model, but also the integration with Energy Plus. So we use the Energy Plus integration with Revit to calculate the cooling loads. Those two at the bottom are ones that are on the list to be developed. Automatic placement of components, which follow a certain structure. and also equipment selection that we can automatically resize air terminals, fan coil units, etc. So here's an example of the Dynamo script. You see it's really not complicated. We just have here we selected the family that we want to work with. Here we select the two names of the parameters in the space and in the family. Here we check in which space every family is, and here we just put the parameter value into the equipment. So it's not that hard. You just need to know a bit of Dynamo and you can get started. And then the heat loss add-in that we are developing currently. Here on the left side, you can see the analytical energy model, which is very simple here with only 4 spaces. And here on the right side, you see the add-in where we have the input that it's taken from this model. We have the names of the rooms, we have the space temperatures, which is all taken from the Revit model. Again, that same one Revit model where we also do the lighting calculations, where we also do the coordination with the different disciplines, etc. Then the following step in this add-in is the verification step, where we can check every surface of every space. We can also, if we need to, we can change some temperatures or some U values. We can make corrections in here. And then the last output step, I didn't show a screenshot yet because we didn't have a working version yet, but that will show the actual results, the heat loss for every space. And currently we're only calculating transmission heat loss, but in the next phase, we'll also be adding ventilation heat losses, etc. And also heat up allowance that we can have here. We can add heat up allowances, we can add ventilation, we can work with different zones. We're also linking this one to the EPB calculation in Belgium, so that we don't have to manually enter that again based on the same building model. Okay, so those were all the technical aspects about the practical integration of those calculations in Revit. I also want to talk briefly about some human or organizational aspects, which are also quite important if you want to start implementing those calculations or your own calculations in Revit. You have to think about responsibilities and accountabilities between modelers and engineers, because typically an engineer is responsible for calculating sizes. That information is passed on to the modeler, and the modeler is responsible for correctly modeling the information that he has received from the engineer. But if the calculations are integrated in Revit, then you can see that the tasks of the modeler and the engineer come very close together, and they touch and they get mingled together. So it's very important that everybody is on the same page about that. They don't have any modelers that say, yeah, I don't want to do that because it's not my responsibility, or engineers that don't trust the modelers, or the other way around. Of course, you need to have knowledge of your engineering calculations. As I stated before, you need to know all the details before you can do anything. If modelers will be doing some engineering calculations, they also need to know the basics at least before they can apply those calculations, because otherwise it's just a black box, and if they don't know what's happening inside, it can be dangerous. You also have the issue of a knowledge of software. Modelers typically know Revit, and engineers, they typically know standalone calculation software or Excel spreadsheets or paper calculations or whatever. So they will both have to learn a bit from each other. If you want to develop things yourself, you'll have to know some scripting and programming languages or outsource it. The easiest is Dynamo, which is visual programming. Next one is Python, relatively easy programming language to learn. You can easily include it in Revit via the PyRevit add-in, also in other ways, but that's the easiest way that we think, at least. And then there's C# and also some Visual Basic. If you want to actually start developing add-ins, then you need to start actual programming. If you will be implementing calculations in Revit, you will also need to train people or retrain them, because if you implement new ways of calculating, you have to make sure that you retrain all the people involved in those calculations. Modelers were not involved in calculations before, and engineers need to accept that modelers might take over some of that work, and they can spend more time with the client discussing what the client actually wants. Better yet is to involve all interested stakeholders from the start. If you want to start up a process of integrating engineering calculations, it's best to talk to engineers and modelers from the start, that you get their input, you get them involved. If you have some modelers or engineers that know C# or Python, include them in the process, let them program a bit so that everybody starts to talk to each other, and then you get the the best results and the most benefits that we talked about earlier in the presentation. Okay, that was all I wanted to share with you. Thanks for listening in, and maybe we'll talk later. Bye-bye.